All right. So 3 whole seconds and it hasn't crashed. That's great. So let's see where we're at. This is where we left off last time, learning about hypothesis tests. And so we're looking at the situation where we have small samples. We're using the t-distribution. In this case, we had 25 degrees of freedom. What assumption do we need to check before this thing right here is valid? We have the 2 problems of a small sample size. We adjusted for one of those with using t and degrees of freedom. What one still is out there?
Distribution?
Yes, distribution of what? Has to be what?
Individual points.
Good. The distribution of the individual points has to be normally distributed. And how do we check that? Lots of ways.
Probability plot.
Probability plot is probably the best one. So a normal probability plot of the individual data points, we don't have them here, would be good. So now 26 is pretty close to 30. So it's not like 30 is a magic number and 29 you're really, really worried and 30 you're not worried at all, right? It's a continuum. So you're in pretty good shape with 26 data points, but you still got to check. So that was a confidence interval on the mean of a small data set, less than 30 samples. So now we're going to continue on with the same cases that we talked about in confidence intervals. Now we're going to look at the difference between 2 means, and we'll start with a large sample and then we'll go with a small sample, just like before. So we're going to write our null hypothesis. Differences between 2 means would be, well, they are equal to each other, or they're not equal to each other, which could be they are unequal, one's less than, one's greater than. Those are the various alternative hypotheses. So I'll write them down this way. And x and y can be switched around. So I would start writing like that, and then what you'll see is that to make it more amenable to our calculations, we'll just change that to mu x minus mu y equals 0, or mu x minus mu y does not equal 0, and so forth. So we're just moving this stuff over. Because the nice thing about this null hypothesis, when we define a new random variable that's the difference between 2 means, it sets its location at 0. And we can draw our distribution of that new random variable. Then the statistic we're looking at would be what does our data say? The difference between the 2 averages. And then here, I've listed the most typical case where we're saying the difference between these means is 0. But it couldn't have to be. We could hypothesize that the difference between these 2 means is 2 or 3 or whatever. So that's what this delta naught is. That's this hypothesized difference. And it's in your H naught. And most often, it's almost always 0. It's most often, we're most often interested in 0. Are these different or not? So if this is the thing that we're trying to say something about, then that's the noise of that thing. And just like before, it's a linear combination of 2 random variables, 2 means, and so we've derived this many times before, that's the sigma of x bar, sigma of y bar, plus sigma of y bar with the C1 and the C2 squareds, and it's a 1 and a negative 1, so that just becomes 1s, and then the square root of that to get the standard deviation. So we've done that quite a bit. So keep in mind, we always match up these two. We always match up that guy in the numerator with that noise in the denominator. Whether it's a mean, a difference between two means, or what have you. Okay, question?
Sigma x and sigma y, not sigma x bar and sigma y bar.
Correct. That's sigma x and y, because where we get this is we have sigma x bar squared plus sigma y bar squared. That's what it is. And then that, by the central limit theorem, is just sigma x squared over nx. And that's sigma y squared over ny. Does that make sense?
Yeah.
Okay, good. All right, p-value works just the same. Okay, so let's look at this example. So when I read through that, I'll start writing down some information. All right, everybody read through that? Good. So we've got welds, made it with different shield gas. And we're wondering, here's the question, we want to hone in on, zero in on this and say, we're wondering if the diameters of inclusions differ. So here we have it. We have a y bar and x bar. Our data seems to indicate that they are different, right? And our null hypothesis will be, okay, you've got a y bar of 0.37 and an x bar of 0.4, but that difference can be explained by noise. That's going to be null hypothesis. There's nothing happening. It's all explained by random variation. The alternative hypothesis says, no, it really is something happening. And then you got to go back to the question, what is it that we're interested in? Did the question ask, is the CO2 shield gas inclusions, are those greater than the other ones, or less than, or different? And so the key word here is differ. And so from that, we can directly say H1, we're wondering if mu x is not equal to mu y. Does everyone see that? So write in our question that clues us into the alternative hypothesis. And then I think it's easier to write the null hypothesis is, well, they're equal then. And the first time, I would recommend writing them this way and then moving over to mu x minus mu y equals 0. Mu x minus mu y does not equal 0. So because of this, it is a two-sided test. Which means when we get p-values, we're going to take the area in the tails on both sides and add them together. Okay, step 2 is we assume the null hypothesis is true. So now this is the distribution of the difference between two means. So its noise here is that, as we mentioned before. And applying the central limit theorem, we can break it down to the standard deviations of the individual measurements. Next step, we calculate a statistic. What is the difference between two means? It's that. So that's the thing we're trying to get a handle on. That's the signal that we're testing, minus the hypothesized difference, which is 0, divided by the noise, which is right here. So we have sigma x 0.26 squared over 581, sigma y squared over 544. Lots of data points. Square root. We go 1.97. So now we want to take that and get a p-value, which means we look up at our table and say, here's 1.97, what's that area? And because it's two-sided, we add that area. And the sum of those two things, that plus that, is the p-value. So we can just look up, since it's symmetrical, we can look up one of them, find the area, and just double it. So we have over 500 data points. So we have way more degrees of freedom than we would need for a t-test. So this is a large sample, so we're using the z-table. And notice one thing, that if you look at that t-table chart, once you get up above 30, those t-values are very, very close to the z-values. Do you see the 0.0244 for z? Good. So that's the area right here in this tail, and we want to double it. So this one plus that one, so 2 times 0.0244 is right around 5%. So we're right on our borderline, right? We're slightly below 5%, so we would say, for us, we would reject the null hypothesis. Just barely, we would reject HO, accept H1, and that would lead to the diameters are indeed different. And again, it's important to write your conclusion in terms of the question asked and the physical experiment that was done. Okay, before we move to the group problem, I've got a question to ask you. We set alpha equals 5%, right? And we assume the null hypothesis is true, so we draw this distribution right like this, and we know simply by random variation, the null hypothesis, even if the null hypothesis is true, let's say we do this thing about 100 times. How many times are we going to get a z-value that's out in the tails, in this, that will correspond to a p-value of 5% or less? So you've done this 100 times, and let's say the null hypothesis is true. You don't know it, but it's true. Out of those 100 times, how many of them do you think will result in a z-value out here so that we reject the null hypothesis? So alpha is 5%. Are we going to get it right every time? Null hypothesis is really true. And we did this experiment 100 times. And we look at, well, in this experiment, did I reject the null hypothesis or not? That's our question. How many times with alpha is 5% out of those 100 experiments are we going to reject the null hypothesis? 5 times. Everyone get that? 5 times, simply by random chance, we're going to get a z-value that's out there. And if we get a z-value that's out there, we are going to reject the null hypothesis. Everyone get that? Even though it's true.
Wait, so why 5 times?
Because our alpha is 5%.
And we're saying if we were to do this experiment again and again for like 100 times, about 5 times, because alpha is 5, we'll reject the null hypothesis?
Yes. So let's, given by the puzzled looks on everyone's faces, let's start thinking about this. And it's really good to start thinking about this now. So, let's go back, we can simplify it, and let's go back to a test on a mean. And we have some mean value there. And we are going to, this is the distribution of x bar. And when we do an experiment, we're sampling from this distribution. We pull an x bar. Sometimes it drops out down here in the middle, and we don't reject the null hypothesis. And for argument's sake, we're saying, well, let's assume the null hypothesis really is true. This guy is really located there. But what the alpha 5% means that 5% of the time, we're going to pull an x bar from the tails, either out here or over here. So does that make sense? Whenever we do that, keep in mind, we never know the null hypothesis is true. Whenever we do that, we will reject the null hypothesis. So we've just made an error. The null hypothesis is true, but due to random chance, we got a value in the tails and we rejected it. So there's no way around that problem. And when we do that, that's called a type 1 error, sometimes called alpha error. And that means H naught is indeed true, but we rejected it. Well, I'll just say that. And that's going to happen simply by random chance 5% of the time if alpha is 5%. So if we reduced alpha, we could reduce that type of error, right? So think about this. Alpha is the level of evidence we're requiring when we put this null hypothesis on trial. If we require more or greater and greater amount of evidence, then we're going to make this mistake less often. Right? As alpha's further and further out, our signal has to be really, really big before we reject null hypothesis. There's going to be a cost with that also. But does everyone, does that make sense? So we have to live with this. We have to live, okay, 95% of the time we're right, and 5% of the time we're going to be wrong when we do these alpha 5% tests. And that goes into your judgment on choosing alpha. What's the cost of being wrong? If it's really, really critical, maybe you want to reduce that alpha. Now, just looking at words, you guys who have taken philosophy classes, that's one way that we can be wrong. If we sort of flip things around, what's another way that we can make a mistake? One way wrong is the null hypothesis is true, but we reject it. What if we look at the other one? So if what's the way we make a mistake? If the null hypothesis is false, but we accept it or fail to reject it. That will be the other error that we'll talk about later. So the other error that we're going to would be H naught is really false, but we fail to reject it. And that's going to be called beta error. We'll talk about those coming up, but I want to try to, we're going to put a whole bunch of these concepts together really quickly. So I want us to get to thinking about this thing. Alpha error is the easier one to talk about. Beta error is going to take a lot more work for us to understand that. Okay. Keep in mind when we make these alpha and beta errors, we have no way of knowing. All we see is our data, and we do the test, and hopefully we've done it right, and we hope we haven't committed one of these alpha beta errors, but we don't really know. Okay, group problem time. Seems awful quiet without group problem music. But Sean, do you remember when you watched lectures when we did this before? When the music was on, it got really loud, right? On the YouTube stuff?
When you record them, we never play music.
Oh. Okay.
Well, let's give it a test.
I thought I tried that. Okay, so.
This is for Ryan, so I think he would enjoy it.
Oh, okay, okay. I'm glad you went there because I thought you were going with this is for Ryan, so we don't care. But I'm glad you went with this. This is for Ryan, and he would enjoy it. So good.
Now that you
Good.
mentioned it, though.
Okay. All right. Oh, I think I put some new stuff in here. No, I didn't. No, I didn't.
Yeah, it's also for John, too. Who cares about him?
Oh, yeah.
There we go.
John, and John too, yes. Let's try this. Tate, sure.
He'll get good for that.
Hope it's not too loud. I'll turn the volume down here and up here. How's that sound? There.
I was just thinking, it'd be a terrible joke if they started playing hide and surprise somebody.
Surprised him?
Yep.
We haven't. Make sure to do all the steps in the hypothesis test procedure. Define H naught and H1. Yeah. Okay. So you're wondering if one is better. Yeah. So it is. It's going to be one-sided like that.
So then H1 is everything, or H0 is everything, but.
Yeah. You can think of it as writing it as equal to, and then getting the less than sign added afterwards. I think that's. And then if this is X and this is Y, you just want to write it the other way. So this is the bigger one minus the smaller one. Here. Anybody have any questions? Okay. Yeah, sure.
Just for
Well, you're right, and I always think about it in here. You know, what does that mean? A small area? Does it mean you're out in the tails or in the middle?
So I always think of it that way, and you'll never get it backwards.
I just which percentile was our place, if you will, to determine the trajectory.
Okay, alpha is the cutoff. Should we go over this? All right. Okay, so we have regular and premium. So I'll call that X. Also 40. So there's our question, which leads us to zero in on the alternate hypothesis would be mu of y is larger than mu of x. That's the question we're wondering, right? So mu of y is less than or equal to mu of x there. And then I would rewrite these mu of y minus mu of x is less than or equal to 0. And mu of y minus mu of x is greater than 0. At least the first few times, I think it's helpful just to go through those extra steps. Now, we assume the null hypothesis is true. That centers our distribution, which is a distribution of the difference between two means at 0. So y bar minus x bar is our distribution. Therefore, it has a standard deviation. Yeah. All right, then we calculate our statistic. C equals the difference between two means, which is what that's our signal, minus our hypothesized difference, divided by the noise, and we get a z of 2.44. Anybody get that? Okay, So we're out here, and our p-value is, it's a one-sided test, right? So we're only looking at the area in the larger tail. We're not investigating at all if the premium is not as good. We're only asking, is the premium better? So we're only looking in the p-value above there. So the p-value ends up being 0.0073. Everyone get that? So, and our cutoff value, is it listed or do we assume? Does it tell us the level of the test? I don't think so. So, since it didn't tell us, we're just going to go with 5%. And this is much smaller than 5%, which means it's way further out in the tails. So, since p is less than alpha, we reject H naught and accept H1, and we'd say the premium is better. A couple of questions arise would be, well, that's one of these cases where there's a statistical significance, but is it of practical importance? Is that, you know, about 1 mile per gallon difference important enough to pay the extra cost, whatever that is? Or if you're the producer, how much more does it cost us to make premium? How much more can we charge? Is it worth it or not? Another question could be, well, what is the difference between those two in miles per gallon? And the answer there would be a confidence interval. Right, a confidence interval would be, oh, it is 0.9 plus or minus something. And so that would be the appropriate use of a confidence interval to tell you, yeah, you're going to get about this much increase in mileage when you go from regular to premium. And here's the confidence interval on it. Any questions? All right, so let's talk about this error thing again. So let's just jump into an intro to the other type of error. So now we know that 5% of the time we're going to commit this alpha error in this test, which means the null hypothesis is true. When I say the null hypothesis is true, it means that distribution as I've drawn it is located there at 0. Null hypothesis is true. It's really there. And 5% of the time we're going to get a z value that gives us a p-value greater than 5%, or excuse me, less than 5%, and we're going to reject it. So let's now think about the other error, which is a little more complicated. The other type of error we said was this. And first I'm going to move this thing out of the way. The other type of error was beta. And it was H naught is false, but we fail to reject it. And I'm going to move this more. Now let's just look at what those two components of that sentence mean in our drawing here. So we're doing this hypothesis test, and we assume H naught is true, and we draw this distribution as such, right? And so when we're talking about beta error, we do that step also. But now we think, what are the implications of these words here? H naught is false. What does that mean in our drawing? If H naught is false, what does that mean on the drawing? Yeah.
Means that between the 5% interval, like more in the middle is where we're getting the data error like wrong. It's not wrong.
You're getting there. I'm in the very first step of that. in the first step of that, don't you?
H naught is false when it's out in the tails.
Think about how did we draw this distribution located at 0? What did we assume? We assumed H naught was true to locate it here, right? Because that's what H naught is telling us. So if H naught is false, this distribution, is it located here or not? No, it's located somewhere else. So that means it's either shifted this way or shifted that way. So that means if H naught is really false, it might be over here somewhere. I'm going to make this up. It might be here at 2. That's what we mean by H naught is false. We assume it's true and we carry out the right steps in our process, but in reality, it's not there, it's here. So then we sample, when we pull our sample, when we get experiments from it. Do our data come from the real thing that's happening, the real distribution, or do they come with the thing we assumed? Right? The data don't care what you've assumed, right? This is what's really happening. So when we get an X bar, it's going to drop out of this red guy right here, right? So now, if this is our cutoff value, if this is our Z star, we're doing this hypothesis test. We don't know what's happening in this. This red is the real thing that's happening that we can't see. And think about this blue distribution now. If I get a Z value out here, I reject the null hypothesis, right? And in this case, it's the right thing to do because it's false. If I get a Z value on this side, I don't reject it. And that's a beta error because it's really false. We don't know it. I know this is a lot. So if this is the real distribution where X bar is coming from, anytime we pull an X bar from this side of the line, we're going to reject the null hypothesis and we're going to be correct, right? That's good. Anytime we pull an X bar from that side of the line, again, think back to the blue distribution. That's the one we're using to do our hypothesis test. Then we're not going to reject the null hypothesis, even though it's false, and we've committed a beta error. Does that make sense? So then that area represents the probability of getting an X bar on this side of the rejection region, which means we're going to commit a beta error that amount of time. All right, that's enough beta error. Beta error is a lot harder to get a handle on than alpha error. So we're going to keep hitting these concepts a bit over and over. Yeah?
So you wouldn't really be able to calculate beta error then because you'd have to know the actual...
Yeah, good point. You have to actually know where it's located. So when we're going to do this, we're going to ask the question of, well, if the null hypothesis is located at some value, what would be the beta error associated with that? If, yes, to get this started, you have to put this centered about this 2 or whatever number it is to get this. And so I'll try to keep in mind when we're doing this, what are the things, in the real world, what are the things that we're actually going to know and not know? We're not going to know mu or sigma. We're not going to know where this thing is really distributed at. All we're going to be doing is our tests. And then we're just asking these questions of, well, how often are we going to make errors when we do these tests? Okay. Next up, small sample. No real surprise there. Difference between two means, small sample size. We have the same problems. Both sets of data have to be normally distributed. Their individual measurements normally distributed. And we have to use T instead of Z. We have the same alternative and null hypothesis. And we've got the same mess for degrees of freedom that we had before. And we're using T now instead of Z. And just to remind us that we don't know sigma, we have S's in our formula. Okay, instead of example problems, why don't we do these as two group problems to give you a chance to do some more work yourselves? All right, yes. So get together. Yeah, you guys get together. Slide over there and work together. Come on, we have an exam a week from today. Yay. I like to think of exam 1 as the Austerlitz exam. It is like Napoleon, your greatest victory is the high point, and then soon after that, you decide to invade Russia. Things will go.
I guess in the case of Sicily,
Sicilian, yeah.
Battle of Sicily and Battle of Ways to the Dead and so on. I guess we can just have like one trip to giants and that's like the best thing.
That's right. As an actor, I don't think he can play too many other parts, but that was good for him.
That's still one thing to try.
Yeah. Yep. So keep in mind when you always think about that, you know, when P is greater than alpha, what does that mean? Does it mean it's way in the tails or more in the middle? When P is big, whereas is it over here or over here? It's over here. So then what do you think that means? You're closer to this H dot, right? Does that help? I would always, rather than try to memorize if it's greater than or less than, always think about where is that located on your drawing? Okay. Yep.
This is just when it comes to alpha,
Uh-huh.
so like the confidence intervals we think about alpha is almost like 90% confidence. We kind of go out
Oh, alpha? Alpha is the same in chapter 5 and chapter 6. So so 95% confidence interval, we talked about that. Kill this music. So in chapter 5, we had a confidence interval and we used the alpha of 5%. We were saying, you know, here's this interval, it's this wide, it's going to capture the mean 95% of the time. That's at 5% of the time it won't, right? And that's very like what we're doing here in alphas. If alpha is 5%, then 95% of the time we will not commit that alpha error, but 5% of the time we will. And those errors are the same, or analogous in those two situations. So think of alpha has the same meaning as alpha of 5% would be like a 95% confidence interval. A smaller alpha, which would mean you're more confident, or you're requiring more proof in this case. So they're both very, very close, if not really the same. Okay. You guys get that for degrees of freedom? Does everyone have that in your calculator ready to go? Or do you do it by hand each time? I recommend not doing it by hand, but it's just yeah. Yes. Make sure you can write it down. On an exam, I'd want you to write it down and show all the numbers in there, and then if it's in your calculator correctly, then you can get to the right number. But certainly try it out. It'll speed things up. Okay, let's move on to this group problem. There we go. Means and standard deviations are there, so I'm assuming you can calculate those by now.
Buttons, yes.
Yeah.
I have a question when it comes to degrees of freedom.
Uh-huh.
So I plugged everything in and I got 11.96. Is that close enough to call it?
Oh, no, you still have to round down to 11. As much as that is painful. It hurts, I know.
It does, yes.
Did everybody get that? Okay.
I'm guessing our alpha is the 0.02.
P-value is 0.02. Alpha is going to be 5%.
And since it's different, it'd be a two-sided, so we'd be looking at 0.025 as our alpha values.
Yeah, so
Pretty soon.
2.769 minus 2.769. And what are those areas? They're in between 1% and 0.5%, right? Another way to remember the p-value is the plausibility of the null hypothesis. And so it's got a 2% plausibility. So that's pretty small. So we don't believe it. And again, this is saying if the null hypothesis is true, it's very unlikely to get a t-value this far into the tails. It's fair. Our experimental results are very unlikely if the null hypothesis is true. So that's why we reject it.
I'm just trying to actually see where you got 0.02 for p-value.
So on this tail, it's between 0.5% and 1%.
Yeah.
And this one, it's between 0.5% and 1%. So it's between 1% and 2%.
Okay. So,
So
we
less
the
than.
maximum is 2.
Well, you can say.
Because I
You
wasn't
can,
sure if we were supposed, like, if we were supposed to say that if we know that the alpha is going to be 5%, if we just said, like, if it.
you could write it that way as well.
Okay. Because I thought it would just be like our p-value would be less than 5%, therefore we reject H.
Oh, always write what the p-value is as best as you can estimate it. rather than just say less than 5%, because that does give you, the reader, more information as to how close were you to rejecting it or not. And that's more of a communication thing. You think if you're taking these data in this analysis, and then you're going to be presenting it to someone, and well, your alpha may be 5%, they might think an appropriate alpha may be something else. And so by reporting your p-value, they can draw their conclusion, which may be different from yours. Does that make sense? So, okay. Any questions? All right, that's a pretty good spot to stop. So 4 minutes early. As I like to do, we can use this time. Now you guys can talk about your emotions. Anyone have any feelings that they would like to express? Such a general interest in trivia over there. Anyone else have feelings of being tired? Okay, good. So we've connected on an emotional level, and this is going to help the class. So thanks for that.